This video is about goodness of fit tests and also about mixtures of Weibull distributions. The main point is that a Weibull distribution can be fitted to any dataset, but such a fitted distribution should only be used for further analysis if it gives a good fit for the data. Or in other words, you could say if it is likely that the lifetimes of the machine really follow the fitted Weibull distribution. And this is the point where our Kaplan-Meier estimator becomes useful again, because we can now compare the fitted Weibull distribution to the Kaplan-Meier estimator. So we can basically compare the two reliability functions. If they have completely different shape, then you can conclude that the Weibull distribution that we have fitted is not a good way to model the data. And if that's the case, then we could try another distribution, or we could also consider a mixture of two distributions. For instance, two different Weibull distributions could then be mixed into one Weibull distribution. This was our previous example. Dataset is quite small here, and we have also fitted a Weibull distribution, but because the dataset is quite small, you will never get a very good fit. But here I would say that this fitted Weibull distribution, there's no reason to believe that the data does not come from the Weibull distribution. But in general, if the dataset is small, it's maybe difficult to determine whether a fitted distribution is suitable. If you have a larger dataset, then it's more easy to conclude whether a fitted distribution is suitable. So this is an example of a Kaplan-Meier estimator of the reliability function that we could get for a much larger dataset. So you see that we have much more steps downwards here. For that same dataset, we can then also fit a Weibull distribution, and then this could then be what we then get. And here you see that the shape of this fitted Weibull distribution is very similar to the shape of the Kaplan-Meier reliability function. So here the conclusion is that this data is modeled quite well by this single fitted Weibull distribution. In this case with k equal to 2.66 and lab data scale parameter 30.24. This is another example. This is a Kaplan-Meier reliability function, and what we can see here is that this Kaplan-Meier estimator does not have the particular shape of one of the two possible shapes of the Weibull reliability function. That's also confirmed if we are then really going to fit a single Weibull distribution to this dataset, and you see that we don't get a very good fit. So even the best Weibull distribution that describes the data best is still not suitable to model this data. And if that's the case, then something else should be done. So we can use another parametric distribution, or we could consider a mixture of two Weibull distributions. And if we mix two Weibull distributions, then we also basically have a new distribution. And we are doing that here because what you maybe remember is that if the k of the Weibull distribution is at most 1, then the shape of the reliability function is something like this. If the k is significantly larger than 1, then the shape is more something like this. And what we see here in this Kaplan-Meier reliability function is that it starts more like this, and later on we see kind of this pattern. So that could be a reason to fit a mixture of two Weibull distributions in this case. So that's what we are going to do. Then how is that specified exactly? A mixture of two Weibull distributions. We have a probability parameter p, and with the probability a time until failure comes from a first Weibull distribution with parameters lambda 1 and k1, and then with remaining probability 1 minus p, a time until failure comes from a second Weibull distribution with parameters lambda 2 and k2. So in total we have 5 parameters. We have the p, we have the lambda 1 k1, and we have the lambda 2 and k2. So 5 parameters in total. And then the question is, what is the best value for those 5 parameters? In order to determine the maximum likelihood estimation for those parameters, we need the density function of the mixture of the two Weibull distributions, and that's simply the mixture of the two separate density functions. So we multiply a first density function with parameters lambda 1 and k1 by p, and we multiply a second density function by 1 minus p. For the distribution function it's similar, it's also the weighted average of two separate distribution functions, and for the reliability function it's also the same. So here the small f, the capital F and the R are the density function, distribution function and reliability function of the standard Weibull distribution. Based on the data that we have, we can then determine the logarithm of the likelihoods as a function of the parameters. So we start by determining the logarithm of the likelihood of each individual duration, and then we sum all those log likelihoods, and then we have the total log likelihoods. And then if we are going to maximize that function over the 5 parameter values, then we get our maximum likelihood estimation of those 5 parameters. So the idea is similar to fitting a single Weibull distribution, only difference is that we now have 5 parameters over which we optimize. So this is how that looks like in Excel, how that can look like for another data set. So you see that here we have the 5 parameter values that we are allowed to change, and most other things are very similar to what we have seen for the single Weibull distribution. And then the outcome is the following. So what we have over here after using the solver can then also be written like this. So that's the maximum likelihood estimation of our parameters. For this specific example, we can then also write down what the estimated reliability function is. So it's the probability P multiplied by the first reliability function, and then plus 1 minus P, so 0.43 times the second reliability function, and that is equal to this. So if you plug in a value for T here, then you get a probability that the machine that has lifetimes that follow this mixture of Weibull distributions, that machine reaches that age T, so that it survives until that age. We can also make the corresponding graph. So here we have the Kaplan-Meier reliability function and also the fitted mixture of 2 Weibull distributions. And then you see that this fitted mixture of 2 Weibull distributions provide a very good fit for this data set. So for this machine, this mixture of Weibull distributions can then be used for further analysis. So for the optimization of the maintenance policy. Then there is one more note that is important to make, and that is a mixture of 2 Weibull distributions always provides a better fit than a single Weibull distribution. And if you have a mixture of 2 Weibull distributions and then you go to 3 Weibull distributions, then it can provide a better fit. So basically the more Weibull distributions you add, the better the fit becomes. But we should only include a second Weibull distribution if the shape of the first fitted Weibull distribution is completely different from the shape of the Kaplan-Meier reliability function. Because otherwise we get overfitting, and then we basically model things that are only caused by randomness and not because there's really a different shape in the data.